Good morning students. Myself Devendran B, working in Electronics and Communication Engineering department from past 7.5 years. My specialization is signal processing. This semester I will be handling Electromagnetic Waves course for 5th semester students. The course code is 18EC55. Okay. As per the VTU syllabus, the course is divided into 5 modules where we are going to learn all these outcomes. These are the course outcomes of this particular course. Okay. So this is the first course outcome we have written. At the end of this course, the student should be able to inculcate all these 5 course outcomes, right? So course outcome 1 says that present the comprehension of concepts related to electric fields, magnetic fields and electromagnetic waves. At the end of this particular course, the student should be able to present his or her understanding about magnetic field, electric field and electromagnetic waves. This is the first course outcome we have written in order to study this particular electromagnetic waves subject. The second course outcome is apply Gauss law to evaluate electric fields due to the different charge distributions by using divergence theorem. Biot-Savart's law, Ampere's law for evaluating magnetic field for different current configurations. Student must be able to apply his understanding capability in order to evaluate electric fields by using various laws such as Gauss law, Biot-Savart's law, Ampere's law for different current configurations, right? So this is the second course outcome that student can be able to do at the end of this course. Coming to the third course outcome, apply Laplace and Poisson's equations to determine potential and energy with respect to point charge and capacitance using Laplace equation. So again, student need to apply his or her ability to identify the potential and energy as well as capacitance of a particular charge by using Laplace and Poisson's equations. Okay. The fourth course outcome is apply Maxwell's equations for time varying electromagnetic waves in free space and conductors and evaluate power associated with electromagnetic waves. The fifth course outcome says that analyzing the different charges and current configurations to derive static and time varying electromagnetic wave equations. We need to derive mathematical model for both the conditions. One is static condition and another one is time varying conditions. When the charge is at static mode, so what is the response? When the charge is moving, what is the response? Like that we have to analyze the system. This is about course outcomes. Coming to the introduction of this particular course, what do you mean by electromagnetic wave? So in our daily life, we are going to see n number of electromagnetic waves. Coming from the mobile communication to our kitchen household applications, we have seen everywhere the electromagnetic waves. The first example, the more convenient example which we have taken is a microwave oven. See, in that particular oven, it is an electronic device where, so we can heat the cooking items by using electromagnetic waves, by using electromagnetic spectrum, by using microwaves we can heat the things, right? So where the electromagnetic wave concept comes into picture. Again, when we are talking with somebody else, so we are transmitting the speech signal in a space. So electromagnetic waves are carrying information from one point to another point. So how the information carrying is happening? So who is the carrier? So how the signal transmits from the transmitter to receiver? How the receiver receives the signal and convert back to the speech? These are all comes under electromagnetic wave theory. So in order to study this thing, the mathematics is very, very important. Without mathematics, without mathematical models, it is very difficult to analyze these kind of things. It is very difficult to understand this kind of theory. Suppose if you want to live stream a cricket match. So how come it is possible? So from satellite, how this signal comes to the earth? So through electromagnetic waves only. How to broadcast a video conferencing, how to broadcast a FM channel, right? These are all through the electromagnetic waves, through the wireless communication techniques, where the electromagnetic spectrum and electromagnetic waves plays a vital role. Okay. Now, so this is the objective of this particular course to study in this electronics and communication engineering. In order to know about the electromagnetic spectrum and its usage, we are learning this particular course. Okay. So coming to the another example. So what is the difference between electromagnetic wave and sound? So I am speaking now, the voice is reaching to you people. So it is a sound, it is a sound wave, it is a speech. It is reaching you people through the space, air. Now the difference, what do you mean, what is the difference between this sound and the electromagnetic wave around we people? What is the difference? A sound is not an electromagnetic wave because sound needs a medium to transmit from one point to another point. It may be air, it may be water, it may be a conductor. Okay, sound is not an electromagnetic wave because it needs a medium to travel, but electromagnetic waves does not need any medium. So why sir, why it doesn't need any medium? See, in space we don't have air, we don't have water, we don't have atmosphere itself, but still radio waves and other ultraviolet waves can reach the earth, right? So hence electromagnetic waves doesn't need any medium to travel from one place to another place, but sound wave requires a medium. What do you mean by sound wave? It is a pressure which we are generating from our mouth, which we are generating from any source, is passing through the air as a pressure wave. Okay, but electromagnetic wave is not a pressure wave. It is the emission of charges. It is the emission of charges from AC source. It is a combination of electric and magnetic fields, so which are perpendicular to each other. We knew that theory, electromagnetic wave theory, fundamental waves theory. So electric field and magnetic fields are combined together to form electromagnetic waves. So how these electromagnetic waves are combined together and carries information in a communication system, which produces heat in a microwave oven. Okay, these are all comes under in this particular course. We are going to study all these things mathematically, not physically. We cannot able to see the electromagnetic wave through our bare eyes, right? So by mathematically we are going to see all these things. How mathematically we are going to analyze, we are going to understand these things? By using vector theory, by using these laws. What are those laws? Gauss law, Biot-Savart's law, Ampere's law, Maxwell's equations, Laplace and Poisson's equation. These are all comes under this electromagnetic theory in order to understand the background aspects of this application. Got it? So this is the course which plays a prominent role in getting the electronics and communication engineering degree. Okay? We are going to study about vector basics, Coulomb's law and electric field intensity and distribution of charges in different applications. Okay? So let us see the vector basics first. Okay? What do you mean by a vector? A vector is a quantity which has both magnitude and direction. So see here, vector, it is a quantity which has both magnitude and direction, which is represented by a arrow with a arrowhead here. Okay, a vector is represented by a line segment with a arrowhead, which is represented as a tile and tip. So the coordinate of tile is x1, y1 and z1 as considered here. The tip coordinate is considered to be x2, y2 and z2. So as I said earlier, vector which has both magnitude and direction, magnitude can be estimated by using analytical geometrical formula, which is distance between those 2 points is calculated as r is equal to square root of x2 minus x1, y2 minus y1, z2 minus z1 whole square and summation of all those things, which gives the distance between 2 points A and B. So coming to the direction, how the direction can be estimated? Direction can be estimated by using a unit vector. So what do you mean by unit vector? Unit vector is a vector which gives only the direction of a given vector. So because unit vector magnitude is always considered to be 1. Okay, so coming to the next point, so a vector is represented by a symbol F with the arrow mark on the top of the alphabet. This is the symbolic representation of a vector. So in terms of unit vector, this can be represented as a product of magnitude r, that is distance between 2 points r, into the unit vector, okay, which is defined as, r is defined as magnitude of this vector f, so which is shown like this. Okay, then coming to the representation of unit vector a r cap is equal to f divided by magnitude of this vector, which is also represented in this form by using analytical formula. So this is all about the vector basics, which we need to use this concept for defining the Coulomb's law. Okay, then coming to the electrostatics. What do you mean by electrostatics? Electrostatics deals with the principle in such a way that electric charge remains constant and its magnitude and direction remains constant in the changing time environment. This is called as electrostatics. See, electrostatics deals with static charge, that is magnitude and direction of the vector remains constant with respect to time. All the parameters of electromagnetic waves remains constant with respect to time, which is considered to be electrostatics. Okay, then with this simple basics, let us come to the Coulomb's law. So Coulomb's law is defined by using a simple experimental setup, that is, let us consider two charge balls B and A. These are the two like charge balls, positively charged spheres or balls A and B. Then B dash is the equivalent mass weight which is used to balance the mass of B and B dash. This is the wire suspension which is helpful to balance these two spheres. So this is the rod connecting B and B dash, which is a non-conducting rod. So in this experimental setup, in order to define the Coulomb's law, let us approach this positively charged sphere A towards B. So due to the presence of like charges, these two spheres gets repelled each other. So due to the repulsive force, the wire suspension gets twisted, so which creates the electric opposite elastic tension in this wire suspension. As the force increases, the twist also increases. The twist in the wire suspension and the force exerted by these two positively charged spheres are directly proportional. So as the force increases, the twist in the wire suspension increases. With this experiment, Coulomb observed that, so in an electrostatic environment, the electrostatic force offered by any of the charge is directly proportional to the product of charges on the two materials and inversely proportional to the square of the distance between them. So I will repeat, in this particular experiment, so Coulomb has observed that the force, electrostatic force between two bodies, two charged bodies, is directly proportional to the product of their charges and inversely proportional to the square of the distance between them. So Coulomb's law states that, see here, the Coulomb's law states that electrostatic force F between 2 point charges Q1 and Q2 is directly proportional to the product of the magnitude of the charges and inversely proportional to the square of the distance between them, and it acts along the line joining between charges. So mathematically it is represented as electrostatic force F is directly proportional to the product of Q1 and Q2, that is charges on the 2 points, and inversely proportional to the square of the distance between them. Suppose these are the 2 points A and B, which has a charge Q1 and Q2, which are separated by a distance R. Then the electrostatic force F between point A and B is directly proportional to the charge on these 2 points Q1 and Q2 and inversely proportional to the square of the distance between them, that is R square. Okay, this is the mathematical representation of Coulomb's law. So with the continuation of the Coulomb's law in mathematical form, the electrostatic force F experienced by the charge Q1 and Q2 is directly proportional to the product of their magnitude of charges Q1 and Q2 and inversely proportional to the square of the distance between them. So if we remove this proportionality constant, we need to introduce K as a proportionality constant, which is given by 1 by 4 pi epsilon naught, where epsilon naught is the quantity which is called as permittivity of the free space or air. Its value is 8.854 into 10 power minus 12 farad per meter. Permittivity of free space, which is represented by epsilon naught, and its value is given by this. So alternatively, epsilon naught is also defined as 1 by 36 pi into 10 power minus 9 farad per meter. So by substituting the values into this quantity, the proportionality constant K is having the value 0.8898 into 10 power 10. Since it is a constant, there is no unit here. Okay. So substituting these quantities into the given equation, the electrostatic force F is given by Q1 into Q2 divided by 4 pi epsilon naught into R square. This is the equation for Coulomb's law. Okay, this is the equation for Coulomb's law. If we represent this equation in terms of unit vector, then this becomes F bar. This is the vector representation of the electrostatic force. So already we know that the vector is represented as magnitude of that vector into the unit vector, right? With the same fashion, see here, the magnitude part into unit vector gives the vector representation of that force. That force, electrostatic force in terms of vector representation, is equal to the product of their magnitude into the direction. Direction is represented by unit vector. So this is the vector representation of the Coulomb's law. Okay. If the medium between the charges Q1 and Q2 is other than air, other than space, then the permittivity changes to epsilon, where epsilon is the relative epsilon r is the relative permittivity of the medium, and epsilon is given by product of E epsilon naught into epsilon r. Substituting this relative permittivity into this equation, then the Coulomb's law alters like this. Okay. Then coming to the experimental setup in order to represent the Coulomb's law in vector form. So this is the experimental setup. Let us consider 2 point charges placed at position A and B. Let us consider 2 point charges which are separated by a distance r placed at point A and B and origin O. So R1 and R2 are the vectors which are defining for the point A and B. Okay, A cap R12 is the directional vector between point A and B. With this experimental setup, the force acting from charge at point A, that is Q1, charge at point A is considered as Q1, charge at point B is considered as Q2. The force asserting from charge A to B is considered as F12. The force asserting from point B to point A is considered as F21. So in this case, I am considering only F12, the force acting from point A to point B. Okay. So coming to the direction of this particular experimental setup, A cap R12 is ratio of that vector divided by the magnitude. So F12 is given by R12. Okay, so magnitude of F12 is equivalent to the distance between the 2 points, that is R. So magnitude and this quantity is calculated by using this formula, by using the analytical geometrical concepts. So R12 is given by R2 minus R1. As I said earlier, we need to take the difference between these two in order to find out the distance. Okay, so these two quantities have been substituted here to get the quantity of unit vector A cap R12. Then substituting this quantity into this equation, we will get the electrostatic force equation in vector form. This is the Coulomb's law in vector form when charge at point A, that is Q1, force Q of Q1 exerting on point B. Okay, if we reverse this process, then this equation holds good. F12 is equal to minus of F21. This is the equation when the force acting on charge at point A due to charge at point B. This equation holds good for the force acting on point B due to charge at point A. Okay, so these are inversely symmetrical. These two quantities are inversely symmetrical. By using this equation, we can able to see that. Then coming to the final equation, so after substituting those quantities, we know that R is the magnitude of the vector between point A and B, then R is equal to magnitude of R2 minus R1. If I substitute that into the given equation, then equation forms to this form. This is the final representation of vector representation of Coulomb's law. Okay, so coming to the last point, electric field intensity. What do you mean by electric field intensity? We know that a particular electric charge creates a field around it. If we consider this as an electric charge which creates an electric field around it, when other charge comes into contact with this, it exerts a force on them. So which is called as electric field intensity. So coming to the definition of this, electric field intensity at any point in the given electric field is the electrostatic force experienced by the unit positive charge placed at that point. Electrostatic force experienced by a unit positive charge placed at that point is considered as electric field intensity in mathematical form, which can be represented like this. Before going to this, so let us see how this has been defined. So let us consider 2 points A and B. So at point A, the charge is Q, so which creates a electric field around it, and at point B, this is the delta Q, the part of the charge which is developed, which is induced by charge Q, hence it is delta Q. At point B, the charge is considered to be delta Q. That is, distance between point A and B is considered to be R. Then by using Coulomb's law, so electrostatic force F is equal to the product of their charges Q and delta Q divided by 4 pi epsilon naught into R square. This is purely the Coulomb's law. Okay, so we know that delta Q is the unit positive charge, hence its magnitude is considered to be 1. Substituting that into this equation, then the electrostatic force experienced by this unit positive charge is considered to be electric field intensity. Then F becomes E. Understood? See, delta Q is the unit positive charge, hence its magnitude is 1. The moment you substitute delta Q is equal to 1, then force experienced by that unit positive charge is called as electric field intensity. Then F is changed to be E. E is given by Q divided by 4 pi epsilon naught into R square. This is the magnitude of electric field intensity. Okay, then coming to the vector representation, by using the directional vector, that is unit vector, which is given by A cap R, the product of the magnitude and direction, which gives the vector representation of the electric field intensity, that is this equation. Okay, thank you. Let us consider in the next class.